In this section you will learn what viscosity is, how it can affect the propulsion engine of a modern ship. Viscosity is the resistance of a fluid to flow. The classic definition is the ratio of shear stress to shear rate. Imagine two plates separated by a distance x of an area A with the space between filled with a liquid. If you push sideways on the top plate with a force F, and as a result it moves at a speed v, then the viscosity of the liquid is the value of F divided by A, which is then divided by the value of V divided by X. The unit of dynamic viscosity is called centipoise, or millipascal seconds. Since viscosity is the measure of a fluid's resistance to flow, it correlates to the internal friction of a liquid and is influenced by the level of solids and the temperature of the coating, as well as other operating conditions. In general terms, the higher the viscosity, the slower the flow of the liquid. The first viscometer design was a cup with a calibrated hole in the bottom. The measurement involved determining the time it took for the liquid to run out the hole. The force on the liquid depends in this case on its density. So the cup measurement was actually the ratio of viscosity to density. The units of kinematic viscosity measured this way are centistokes. On board ships, we always refer to viscosity in terms of the kinematic viscosity. During the past decade, advances in diesel engine technology have been made to meet the new requirements of burning lower-grade fuel oils. This requires careful treatment and makes the installation of a suitable plant necessary. According to present techniques, the most effective way of cleaning liquid fuels from solids and water is achieved by using centrifugal separators. The temperature of the oil also determines its viscosity in addition to the oil's composition. A consistent viscosity is maintained by the viscosity system, which consists of a viscosity sensor, controller, and a heater cabinet. The viscosity controller regulates the viscosity. The viscosity sensor measures the viscosity. Modern devices work on any one of several principles. Some impart a magnetic force on a piston and measure the speed. Another device uses a heavy piston and measures the speed, whereas others rotate a cylinder inside a coaxial sleeve and measure the drag force on the sleeve. Some devices vibrate and measure the attenuation, which depends upon both the viscosity and density. Other devices work by forcing the liquid through a small hole at a controlled flow rate, then measuring the pressure across the hole in order to calculate the viscosity. What is wrong with the traditional approach to measuring viscosity? The most common measurement method has been to dip a cup with a specific shape into a coating reservoir, take it out, and then measure how long it takes for the fluid to flow through a hole in the bottom of the cup. The longer it takes, the higher the viscosity. Unfortunately, this method is inaccurate. 10 different operators will get 10 different measurements. With the viscosimeter, you can measure the time in which a certain quantity of fuel flows through the meter. Until 1977, it was common to use redwood seconds, measured at 100 degrees Fahrenheit, when measuring the viscosity grade of intermediate fuels. The problem with using 100 degrees Fahrenheit as a reference temperature is that fuels with very high pour points may have non-Newtonian properties at this temperature. This means that the viscosity temperature lines will not be straight in the lower temperature range. Therefore, viscosity should be measured at a higher temperature. Fluids that have the same viscosity, regardless of shear rate, are considered to have Newtonian properties. With non-Newtonian products, there is no longer a linear relationship between shear stress and shear rate, and this contributes to the non-linearity of the flow equations. In other words, they do not have a constant viscosity. Centistokes, measured at 50 degrees Celsius, has become the standard of measurement since 1977. An IFO 180 grade fuel is a fuel with a viscosity equal to or less than 180 centistokes at 50 degrees Celsius. To the dismay of people finding it difficult to adjust their thinking from seconds redwood to centistokes at 100 degrees Fahrenheit and 50 degrees Celsius respectively, the committees dealing with new fuel standards suggest 80 degrees Celsius or 100 degrees Celsius as the reference temperature of the future. Engine manufacturers nowadays often use centistokes at 100 degrees Celsius. The reason for increasing the reference temperature is that it has become general knowledge that the viscosity index of secondary refined fuels may differ from the traditional fuels. That is why it is important to measure viscosity near the temperature at which the fuel is to be used, i.e. the injection temperature in the case of diesel engines. In addition to centistokes and seconds redwood, there are some old viscosity standards, such as seconds Seabolt universal and Engler by 20 degrees Celsius or 50 degrees Celsius. One commonly asked question is, how do I convert centistokes to centipoises? If you are working with hydrocarbons like fuel or lubricating oil, the conversion is simple. In order to calculate centistokes from centipoise, divide it by the density. Since most hydrocarbons have a density of about 0.85 to 0.9, the centistokes value will be about 10% to 15% higher than the centipoise value. Of course, to do the reverse, multiply centistokes by the density to get centipoise. For converting centistokes, seconds redwood, Engler and Seabolt universal, you can use a conversion table. A modern diesel engine is designed for efficient combustion and optimum power output when burning fuels ranging from 30 centistokes at 50 degrees Celsius to 700 centistokes at 50 degrees Celsius, provided that the fuel is properly treated and conditioned. The fuel injected into the engine must meet specific pressure, temperature, flow, and viscosity requirements. Efficient fuel combustion can only be achieved if the fuel temperature and viscosity can be controlled within recommended limits. Today, many modern diesel engines are capable of burning heavy fuels with viscosity as high as 700 centistokes at 50 degrees Celsius. In order to prevent damage to the injection pumps and achieve optimal combustion, it is important to maintain the correct viscosity of the fuel going to the injection pump. Temperature control alone is not sufficient due to individual differences in oil characteristics from one bunker to another. Injection of fuel into a diesel engine at the incorrect viscosity can have a number of adverse effects on the engine and its performance. A high injection viscosity fuel, in excess of 20 centistokes, can cause poor combustion in the cylinder of the engine, contributing to a build-up of deposits on exhaust valves and piston heads, and an increase in lubrication oil contamination. Another problem that can have very serious consequences is the effect of large and rapid changes in fuel oil temperature on the injection pumps. Without accurate viscosity measurement linked to temperature control, the heaters may fail to react properly to changes in fuel properties and engine load. This could result in a seizure of the pump cylinder liner and the plunger due to the varying thermal expansion properties of the liner and the plunger. Engine manufacturers have improved engine designs to cope with this problem by, among other things, developing new fuel injection pumps and nozzles to compensate for viscosity fluctuations. However, accurate viscosity control and fuel oil treatment is required. Most viscosity sensors operate on the principle of pressure drop measurement across a capillary pipe. After reading the pressure drop, the viscosity is calculated using a formula. The problems inherent in this technology are correct measurement of the pressure drop, transforming the measured pressure drop into a correct viscosity value by calibrating the instrument. The pressure drop is a function of pipe diameter, pipe length, flow velocity, density, and viscosity. In order to measure the viscosity, all other parameters must remain constant. Therefore, it is imperative that the pipe diameter does not change due to clogging or fouling. The flow must also remain laminar, in other words, streamline, without any turbulence when it is passing through the pipe, and the flow velocity must remain constant. This means that the pump, capillary pipe and pressure gauge must be checked and serviced regularly to ensure that measurements are correct. Any change of instrument setting or component parts of the system will require that the unit be recalibrated. Heavy fuel oils are usually contaminated with solids and water. Should unclean or insufficiently treated heavy fuel oil enter the engine, it can cause unacceptably rapid wear on engine components, such as piston rings, cylinder liners, fuel pumps, fuel valves, etc. Furthermore, excessive sediment can collect in the combustion process. Sodium in particular, which originates from seawater, can be found in the fuel oil. This leads to the formation of deposits on pistons and in the turbocharger. For this reason, water must be carefully separated from the fuel oil. Settling tanks are used for the first stages of treatment. They can, however, only perform a coarse separation, such as freeing water from the heavy fuel oil. In order for them to be effective, settling tanks must periodically have the sludge and water that accumulates in the bottom of the tank drained off. Most cleaning is performed by optimally dimensioned and correctly adjusted and operated centrifugal separators. Modern designs make the adaptation of the gravity discs to varying densities of heavy fuel oils in use unnecessary. Today's machines automatically expel the sludge from the centrifuge. For modern power plants designed for burning heavy fuel oils of the lowest grade, such centrifuges and a viscometer are absolutely necessary. This is particularly necessary when heavy fuel oils are being used. Homogenizers can improve combustion properties to some extent. They will, however, be of no help in the removal of solids from the fuel oil. They should therefore be regarded solely as auxiliaries in the treatment plant. Filters retain solids of a specified size and shape. They are, however, practically useless in retaining water. Water can even attribute to accelerated clogging of filters. Due to previous experience, engine manufacturers recommend the use of separators for the treatment of heavy fuel oils. Separators work on the principle of centrifugal force instead of the gravity force. Modern separators, without gravity discs, can separate poor quality oils at a relatively higher throughput rate, approximately 1010 kilograms per cubic meter at 15 degrees and 700 centistokes at 50 degrees Celsius. In older treatment plants, you will find separators with replaceable gravity discs, which must in each case be adapted to the density of the heavy fuel oil to be treated. The correct size of the gravity disc must be selected according to manufacturer specifications. Operating centrifugal separators as purifiers and, if necessary, clarifiers arranged in series is also recommended. Almost all separators on board a ship are self-cleaning separators. The separating effect, such as the cleaning efficiency, depends upon the throughput and on the viscosity of the heavy fuel oil. As a general rule, The smaller the throughput and the lower the viscosity of the heavy fuel oil, the better the separating effect. It is necessary to heat the heavy fuel oil before it enters the separator and maintain the working temperature at a constant level within a tolerance of plus or minus 2 degrees Celsius. The minimum required temperature depends upon the nominal viscosity at 50 degrees Celsius of the heavy fuel oil. This temperature can be found in a viscosity temperature diagram. Also check the instructions from the manufacturers of your separator. For design reasons, the admissible heating temperature is sometimes limited. The sludge removed by the centrifuging must be removed periodically from the separator drum. In the case of self-cleaning separators, the emptying sequence process may be controlled automatically. But even in such plants, operating personnel must monitor the correct function and the frequency of these events. It is of great importance that the drain of the drum is open and kept free from sludge, so that unacceptably high back pressure does not affect the operation of the separator, thereby adversely affecting the cleaning of the heavy fuel oil. Periodical inspections are necessary in order to make sure this does not happen. When the fuel viscosity is too high, excessive pressure is produced in the injection system. This can cause parts of the injection pumps or their drive to be damaged or cause the relief valves to spray off. The atomization of the fuel oil is also affected, and this results in incomplete combustion. The viscosity of fuel oils can be reduced by heating the oil. This diagram illustrates a typical ratio between viscosity and the temperature of various heavy fuel oils. This diagram also shows the temperatures that are required to lower the viscosity of various heavy fuel oils down to the value required at the inlet to the injection pumps. This temperature is generally called required heat-up temperature. The viscosity controller regulates the preheating of the heavy fuel oil. In order for the engine to run smoothly, irregular vapour must not be allowed to collect in the injection pump. Because of this, the preheated heavy fuel oil is fed into the injection pumps under pressure by the high-pressure booster pump. This pressure must be set at the pressure regulating valve. Most new main engines can be started on diesel oil or on heavy fuel oil and manoeuvred on both. It all depends on your engine type. When starting on heavy fuel oil, sufficient heating energy must be available. If this is not available, the engine must be started on diesel oil. A switchover to heavy fuel oil may only be made when the required viscosity is obtained. If the availability of sufficient heating energy is not guaranteed, operation must again be switched back to diesel oil before shutting the engine down for a longer period of time. After operating with a low load, the output should be raised gradually. Switching to diesel oil at an early stage to flush the system is recommended when work on the engine's fuel system is scheduled at the next stop. The day tanks must be dewatered and desludged at regular intervals. In order to maintain their effectiveness, tanks must have the sludge and water accumulating in the tank bottom periodically drained off. The cylinder cooling water must be heated. Check the manufacturer instructions. The viscosity of the heavy fuel oil before the inlet to the injection pumps must be brought to the required heat-up temperature. It is also a good idea to circulate the bearing lubricating oil through the separator for a while before starting. When operating and manoeuvring on heavy fuel oil, the fuel temperature and viscosity must be kept at the specific values, as well as the temperature of the fuel valve cooling water, if it is in use. The heavy fuel oil booster pump must be kept running, so that the fuel can circulate at the required viscosity through all of the injection pumps. The booster pumps can only be stopped after switching the system over to diesel oil, and when all of the heavy fuel oil has been removed out of the system. The cooling water to the injection nozzles must be kept at a specific temperature. Cylinder cooling water should also be kept at a specific temperature. Pre-lubricating pumps or standby pumps for bearing lubrication must be running. The fuel oil circulation systems cannot be stopped when running on heavy fuel oil. Before switching over, it is necessary that the diesel oil in the injection pump is heated to a specified temperature. That heat up should be gradual. A rapid rise in temperature can lead to seizure of the injection pump plunger. It is therefore recommended that the heating steam only be allowed to flow first to the preheating of the piping, the fuel filter, etc. In this case, the viscosity controller can shut off. The fuel temperature can then be controlled manually. Quick temperature rises must be avoided. The operation with hot diesel oil should continue at least until the injection pumps are warm to the touch. Then a three-way valve can make the switch from diesel oil to heavy fuel oil. When equipped with a proportional three-way valve, the viscosity controller will control the heater when switching over gradually, and the controller does not have to be switched off. Subsequently, the steam, thermal oil admission or electrical power to the heaters must be increased. When the fuel temperature is brought to the required preheating temperature for the respective heavy fuel oil, the viscosity controller can then again be switched on. The heating to the fuel filter and fuel piping should be kept on at least until the required preheating temperature on the engine has been achieved. It is often recommended that it is not to exceed 75% of the maximum continuous rating load during switchover, until the required preheating temperature has been reached. Before the switchover, the three-way valve must be turned, or the proportional three-way valve must be switched over gradually. The buffer unit, or mixing tank, now contains a mixture of heavy fuel oil and diesel oil. The viscosity of the circulating mixture drops rapidly as the diesel oil ratio increases. The viscosity controller will subsequently close the steam or switch off the electrical power to the heater. If the temperature is at a minimum value, the viscosity controller and/or sensor may be switched off if required.